Yeah. Right. So I decided I changed my title completely. We actually just did a press release on this result, and I was talking to some reporters yesterday, and I realized that I had never actually given a talk like talking to scientists about it. And so maybe I should try that before I, but it's kind of a gee whiz result a little bit, but I also think it's fun and interesting. So maybe last talk of the meeting it's a good one to do, and maybe I'll finish early even. So this was all inspired by the LIGO result that you probably heard about. We're probably going to get some Nobel Prizes from this, but about a year ago, the LIGO team announced the detection of this gravitational wave signal that was detected with roughly a few millisecond delay between two different detectors across the country, where they saw this amazing ring down signal that looks sort of exactly like the GR calculation said that emerging black holes should look like. So it's sort of an astounding, amazing result. Flash forward a couple months ago, they announced yet their fourth detection of massive black hole binary merger. And here's the Hanford and Livingston signals. These are shifted by 3 milliseconds and the signals, agree and lie right on top of each other. These black holes are about a gigaparsec away. They were able to figure out roughly how far away they are based on the sort of timing, and they have some rough sense of where they are in the sky. And here are the pairs of black holes and the 4 gravitational wave signals and where they sit in that M1, M2 diagram. So one of the things that's kind of interesting is if you look, for example, in the most recent gravitational waves that they saw, here's mass 2 and mass 1, and you see the masses of those black holes are big, right? So these are something like 30 solar mass black holes that are merging, and that's a big number, right? That's big. And I remember when we first saw those came out, we were sitting in the archive discussion talking about it, and we're just like, that seems like a big black hole. How many black holes are there? What does this take? So in a couple years, they've discovered a few of these big black hole mergers, and the massive black hole merger rate is something like a few per gigaparsec cube. So that's these things, we see them out to a distance of a gigaparsec. We've seen a few in a couple years, and that they're able to derive a merger rate more precisely than that. And the overall total black hole merger rate that they estimate is something like 100 per gigaparsec cube per year. So that's the rate. So this is one of their press release images, but you know what? So these are the different black hole merger candidates they've seen, these sort of big. And so on this axis, it's how big the black holes are in solar masses. And as I said, these are big numbers. So these 30 solar mass black holes, people were sort of scratching their heads, I think, initially, and thinking, where are these come from? Is this expected? Do we need to do anything special to explain this? And in fact, there have been a number of papers that have said, are we detecting dark matter, right? Because I don't know, maybe that's easy to write, but these things are big, and maybe we're seeing primordial black holes, and it turns out there's a small window where it's possible these could be the dark matter, and they had, within these scenarios. So this is sort of the context of this. So what we sort of wanted to do is sort of run through the exercise ourselves and say, look, how many of these big black holes should there be, and do we have to do anything weird to explain this? So that's the impetus of this. So there's all kinds of the ingredients for doing this calculation. So what we basically have done is a counting exercise. We sort of put together all the things we know about galaxy formation, galaxy evolution, and stellar evolution, and put it all into the pot and stirred it up and try to get a number. The first thing we want to do is just find out how many black holes there are. So here are predictions from 2 stellar evolution codes, Star Trek and Parsec. And what the question is how big does your initial star have to be in order to make a black hole bigger than 30 solar masses? And so the upshot of this is that as a function of the metallicity of the star, as long as the star is pretty low metallicity so that it's not losing a lot of mass over its lifetime, you actually don't need that crazy big of a star to make a 30 solar mass black hole. So as long as the metallicity, for example, is lower than about minus 0.5, you can have a 30 solar mass star and it turns into something like a 30 solar mass black hole. So that's not insanely large. And you can do this for different different size stars, and so if you need a 50 solar mass black hole, then you have to go even to lower metallicity. But a 10 solar mass black hole, actually, you don't really have to go that low in metallicity to produce a black hole that big. And so if you have that, then we know, of course, what galaxy, if we want to talk about a global population of galaxies, we know what the metallicity M-star relation is. Okay, the stellar metallicity versus M-star. So if we're looking at a population of stars, we have some sense of what fraction of those stars formed at low metallicity. So for dwarfs, right, this is easy. Almost all their stars are very low metallicity, and so you would think, given some IMF, there's going to be a lot of big black holes per star. So specific rate of black holes is going to be pretty high in these little dwarfs. But even in big galaxies, right, there's going to be some tail of low metallicity stars that would have some specific massive black hole population that you could turn the crank and determine. So if you go through this exercise, you can do things like this. So this is the number of big black holes you expect as a function of galaxy stellar mass. And the points along the middle are, basically we're counting black holes bigger than 30 solar masses. And the color code is just the metallicity. And what you notice is that at low metallicity, it's sort of a 1-to-1 relation. And it's something like every 1,000 solar masses of stars you form, you get a big 30 solar mass black hole. So what that means is Draco has about 100 of these things, and the Milky Way has millions and millions of these things. So there's lots of these big black holes. So up to about L star, up to about the Milky Way, you get this 1-to-1 relationship where the number of black holes goes like the mass of the galaxy. And then on the other side of that line, you just start running out. Basically, the stars are too metal rich. So the stellar populations become so metal rich that you start cutting off your populations of really massive stars. So the dashed line is 50 solar mass black holes, and the solid line is 10 solar mass black holes. So above about the mass of the Milky Way, you really don't have that many very massive black holes per galaxy. And then for lower mass black holes, you do. But you can turn the crank and do these calculations. So now we know how many black holes there are per galaxy. Then you just multiply this by the galaxy stellar mass function. You can get a global black hole. Right, I said this already. You can get a global number density per galaxy now. So this is, in the cosmos, what fraction of black holes of a given mass live in a galaxy of a given size. So what you see is most small black holes live in L-star galaxies. Most stars live in L-star galaxies. So that's one thing you see here in the dashed line. The dotted line, this one here, this is 50 solar mass black holes. They are living like in LMCs. And then there's sort of this tail down to dwarfs. So you can integrate this differential function and get a cumulative global count of black holes. And that's what's shown here as a function of black hole mass. And by the way, here are two different IMFs. So if you do this for two different IMFs that are pretty different, a Krupa and then an IMF that Marla had proposed that basically changes, basically you have more low mass stars and low metallicity galaxies, you're getting like factors of 2 different. So it's not a huge effect actually on the IMF. So this is just the Z = 0 global black hole count. So if you do something really naive, right, and you say, look, the LIGO merger rate's about 100 per gigaparsec per year, you need 1 out of every 5,000 black holes to merge every giga-year. And factors of, oh, it's darn, factor of 2. Yeah, you got to redo the whole calculation. Yeah, so you got to do 2. That's right. You need a pair of these things to merge every giga-year out of 5,000. You can do things a little bit more carefully. I'll go through this pretty quickly. But for example, now if you want to ask some things like, what's the number density of black holes that are available to merge? You do things a little bit more carefully. We know the number density of all black holes. That's what we just calculated. And that's a very solid number, factor of 2-ish. So that's pretty easy. Then you don't know a lot of other things, right? So then there's some fraction of these things that are born in binaries that will eventually merge in a Hubble time. These are things you don't know. The fraction born in a binary is probably pretty high. It's probably about 0.5 because massive stars have a very high binary fraction. So this is probably pretty of order 0.5 or so. Those that survive the stellar evolution process after the supernova blow up, we don't know. I mean, there's people that work on that, but we just have totally just punted and sort of absorbed all of this stuff into a number we call epsilon merge. So this is sort of like the binary fraction of things, black holes that are born and eventually merge in a Hubble time. And this number should be between 1% and 0.1%, you would naively think, just based on back of the envelope. So this is the number density of black holes that eventually could merge. Then if you want to calculate the merger rate, then you have to go a little bit further. You actually want to know what the black hole birth rate is. And that we link to the star formation history of the universe via the McDowell plot. So we're sort of multiplying things together. And then you have a delay time, so they're born and they take some time to merge. And so there's some probability distribution of delay times. Because we're doing something very simple, we assume that's a delta function, just because we wanted to understand what we're doing. And then if you do that, you get a rate. And the rate is just linked to the black hole birth rate with some shift based on how long it takes these things to merge. So the two parameters in our model that we don't know their answer are how long it takes an average black hole to merge, a black hole binary to merge, and what fraction of black holes are born in binaries. These are two numbers that we don't know. And we can ask, what do we need to do to match the LIGO signals? And basically, this is it. So if the fraction of black holes born in binaries that eventually merge in a Hubble time is 1%, you get the black line. And this is the merger rate density versus the merger time scale. The shaded region is the LIGO results. This is all black holes. In this particular case, it's all black holes, but you can do it, yeah. How do they know it? So they basically assume pretty much what we've assumed, that there's an IMF and you have a power law down to, I mean, they've measured things at 10, so you don't have to go that much farther. But they also do things by 30 solar mass, 50 solar mass, or 30 solar mass, I think 10 and 5. But it's all consistent at all scales. So this is kind of where you are. And you see for reasonable numbers, all of these numbers are pretty reasonable. It's easy to get the answer. So, you know, that's sort of the first result. You don't have to do anything that crazy to match the LIGO result. And then you can, you know, if you really want to, you can say there's some degeneracy between the binary merger efficiency, that's epsilon parameter, and the merger timescale. And the point is that if the merger timescale is long, of order the Hubble time, then you need a lower efficiency, because basically what's happening is these things are being born at the peak of the McDowell plot, and then they just happen to be merging today. But if the other extreme is it only takes them 100 million years to merge, that means they're being born now when the star formation rate of the universe is fairly low, and so then you need a higher efficiency of these things born in binaries to merge. So there's sort of two general classes of models. There's prompt mergers and there's long timescale mergers. And we don't know right now which is which. So then what's left is, okay, what can we do to figure out which is which? So are these things merging, are they born and merge immediately? And so we're seeing them right after birth? Or were they born a long time ago and took a long time to merge? And so a way you can crack that code is if you can begin to triangulate the host galaxies and map out the host galaxy mass distribution, you can start to answer this question. So the upshot is, if you have prompt mergers, then you're seeing star formation, basically. And so you should see these black holes merging in dwarfs. So there'll be most of these things will live. This is the galaxy host mass. This is the merger rate density per host mass. So while the global merger rate you measure right now is the same for both of these models, where the mergers are happening depends on whether or not you have prompts. If the mergers are prompt, you're going to see them in dwarfs. If the mergers take a long time to happen, you're going to be seeing them in giants. And we predict different distributions depending on whether it's a big black hole or a little black hole, even within these models. So the nice thing is, if you think of what are we going to do with gravitational wave astronomy, this is one thing you could think about doing. And then you start to refine models. You start to sort of test evolution models. Okay, are they prompt mergers? Are they not? These kind of things. Okay. I should add that I've put on neutron-neutron star merger rates as well. These things hopefully are going to have electromagnetic counterparts, and so it might be easier to do this, you know, eventually be able to do this kind of break them up into host galaxy mass if you're measuring these things as well. There probably are a lot of other things to do once you start folding in neutron star mergers. You can do R process element production and this kind of thing in the context of these semi-empirical models. All normalize and staple to the LIGO results, right? So you sort of know that the global integrated rates are right, or at least, you know, once LIGO results get tighter, you can staple them to that. Okay, right. So if you could determine the host galaxy masses of merging black holes, if you see that they're living in dwarfs, this suggests these are prompt mergers, and you have efficiency binary formation. If you see them mostly living in massive galaxies, that means these are cosmological merger timescales, and that you have fairly inefficient binary formation and survival. So these are the kind of things you begin to learn about these populations. I should say that, so Shea is working on related stuff, and this was a paper that they put out, Lamberts et al., where they're trying to do sort of forward modeling on these kind of things. But qualitatively, our results sort of agree in that they're finding, you know, you should have populations with dwarfs with shorter merger timescales, and the more massive galaxies will have longer merger timescales, and sort of that's consistent. Their approach was actually to forward model the whole thing using a more sophisticated, I think, approach. So this is these are the results. These are my conclusions. Big black holes are common, so you don't have to do anything weird to explain the existence of these massive black holes. There should be like 100 of them in Draco. The Milky Way should have 10 million of them. There should be all kinds of these things in the stellar halo, the Milky Way, etc. It's easy to explain the LIGO merger rates. You don't have to do anything that weird, and things actually fall out fairly naturally once you normalize to these numbers, which you can calculate semi-empirically. And in the future, one of the interesting things is going to be try to figure out how to do this triangulation, and using the depth and using maybe clustering statistics and other things to try to sort of get a sense of what kind of galaxies these things are living in. I put this up here before, and I think this answer is definitely no. Okay, that's it. Thanks. Wow. Okay. Joel?
Well, a quick comment. LIGO actually has only been on detecting for a few months, and their detection rate is around 1 a month, I think a little less. But they're pretty sure they can get a factor of 2 improved sensitivity, which means they get a factor of 8 higher merger rate. And they might be able to get a factor of 3. So in other words, we're going to be getting detections every week in a few years, and every day a few years after that. And of course, with the extra, the 3 more such detectors that will be operating, we'll have a better triangulation, but not good enough to tell the galaxy without the much magnetic signal.
Yeah.
And my question was, a puzzle, if you look at X-ray binaries, is that the neutron star, ordinary star binaries give you neutron star masses with few solar masses. And then there's a gap. And the more massive one, the black hole binaries, that black hole ordinary star binary, because the black hole binary, you don't see anything. But there you get masses of 8 and not high.
Yep.
So is the fact that we're not seeing that in any kind of contradiction with the median that you think are in the Milky Way?
So
or can you say anything at all about how many you expect? Because maybe half are in the binary, the other half are possibly going to have an ordinary star.
Right. So we haven't done that. Right.
The ones that are in binary must have at one point had an ordinary, a red giant that then became a black hole after it also collapsed. And at some point they had to have common envelope evolution probably to stay together.
Right.
But they should be detectable.
Yeah. Right. So we have not done the calculation in our sort of simple scenario how many you would see in some X-ray binary survey. But that's something we should do and would be very interesting to do, but we haven't done it. But yeah. We'll just, yeah.
There are so many massive black holes. Why they are not detected? Why they were not detected
as machos? So it's not even, it's like, so for example, there's one, basically you get one of these per 1,000 solar masses of stars. Okay, so in the stellar halo, for example, there should be 1 million. If you multiply that by 30, it's still, 30 million solar masses. That's way, way below the dark matter. And so what basically the macho constraints were that, it has to be less than like 1% of the dark matter. This is way below that. So this is consistent with those gravitational lensing constraints and that kind of thing. So it's sort of frustrating. It's not clear exactly how you would see them, but it is consistent with that. Yeah. Mm-hmm. Yeah, I mean, you know, I mean, we haven't, you know, taken this to the nth degree and seen all these things, but it would be kind of fun to think about these. I mean, at some level, people sort of have thought about, okay, you start with 100 solar mass seed and then you run with it, but I don't know if people have kept doing it all the way down the chain. I don't know. Yeah. Yeah, so we haven't done too much carefully with that. So the one thing we were able to do, it was much easier to do the calculation if you do the constraint on both black holes being more massive than the same mass. Then the things become much simpler, and those were the first calculations we did, and those were the first constraints we compared to. I'll say this, one thing we did predict is that certainly within the next 5 years, there should be detections of 50 solar mass black holes merging, or that would be weird. We didn't do this sort of luminosity completeness saying, okay, we haven't factored in the sensitivity stuff to say how many 5 solar mass mergers should be seen. Right. That is consistent with the rates that they derive. That is consistent because they're just so. I can't remember the mass. Shay and I were talking about this. The energy of the merger scales like the total mass to a power higher than 2, I believe. So it is very strong. So these are just like the brightest things in the universe. They saw them first, and that is consistent. So it's not that weird that they haven't seen. They have seen a 7 solar mass merge with like a 15 or something, and I think all of that is consistent. Yeah.
In principle, these black holes may have already done some merger effects, and so they could have already grown by mergers rather than being born at these masses.
Well, then they have to get in a binary again. I mean, you could recapture something, but we didn't include that. So these are all first-time mergers in our calculation, at least. Could be wrong.
So maybe I should know this, but I don't. Until say that the merger of the 230 solar mass black holes, how far out am I able to detect that? Like at what redshift?
It's like Z of 0.2, something like that. Yeah, something like that. Is that right? Shay, do you know? Were you going to say something, Shay? You
Well, yeah, so I was going to say, I like that you were saying ends up coalescing, but I think that the worry there is that really both
Yeah.
have both and black holes that get captured globally for a very long time center binaries that form close together and don't break the stars. Binaries that form far apart and get along.
Yeah. I mean, I guess one question would just be, I mean, this is sort of a toy model at some level because there's like one extreme versus the other extreme, and the answer is usually in the middle. But you could argue that just a priori, wouldn't it be odd if all of those populations mixed up to be about equal? Wouldn't there, I mean, devil's advocate, wouldn't you be more likely to be dominated by prompt or dominated by slow? I mean, I know you guys have run these models more specifically, and maybe it is about 1-to-1, but it's worth looking at least.
Prompt versus the slow. I mean, it really boils down to what the initial separation of the binary was, right? I mean, everything else is just things like GR.
So that's right? True if you're only talking about.
You're talking about what?
You're only talking about. Actually, that's not quite true because you still have spiral string set. So endlessly still matters there. Possibly just like coming. How quickly that GR